Hi everyone, what's up? Welcome back to my tutorial channel. Today I'm gonna continue to talk about the Scholes option pricing model. In this second part, I'm going to talk about some assumption underlying the Scholes models, some calculation and some application. The targets of this lesson is to recognize the assumption underlying the Scholes model, estimate the stock volatility from past stock price data, use the Scholes formula to value the European cars and put on stocks with no dividend, continuous dividend, discrete dividends, currency and future contracts. So let's start with some assumption underlying the Scholes models. In this lesson, we introduce the Scholes formula and discuss some simple application of it. So the assumption underlying the Scholes model here will basically depend on what type of models that we use. And in this lesson, I want to introduce the binary option. A binary option is also called all or nothing option, and there are four types of it. The first type is cash or nothing call option. This option pay 1 at time t if the stock price is greater than the try-K and pay nothing otherwise. In order to value the payoff function, we use the indicator function I, st greater than k. This function returns 1 if the condition is met and returns 0 if the otherwise. And the expected payoff is just we take the expected value of the indicator function. So it should be equal to probability that the stock price is greater than K. And from the last lesson, it should be equal to phi of D2 hat, where D2 hat here is natural log of S0 over K minus alpha minus delta minus sigma squared over 2 times T over sigma squared of T. You can rewatch my last video to understand what is alpha, what is delta, and what is sigma. Under the risk neutral measure, the expected payoff is given by expected star of the indicator function, and it should be equal to probability that the stock price is greater than K, and it is equal to phi, capital Phi of D2, where D2 is natural log of S0 over K subtract R minus delta minus sigma squared over T over 2 in the parentheses times T over sigma square root of T. Here D2 and D2 hat is different at alpha and R. So in order to obtain D2, we basically replace alpha with R. And the price of this option is e to the minus RT phi of D2. Assumption underlying the Scholes model. The second model is cash or nothing put option. So the last option was call option. Now we consider put option. The put option pay 1 at time t if the stock price is less than the strike and nothing otherwise. So the payoff function, again we use the indicator function. I of s of t less than k is equal to 1 if the stock price is less than k, and 0 if the stock price is greater or equal to k. The expected payoff is the expected value of the indicator function, and is equal to the probability of the stock price less than K, and is equal to phi of minus D2 hat, where D2 hat is natural log of S0 over K minus alpha minus delta minus sigma squared over 2 times T over sigma squared of T. Under the risk neutral measure, the expected payoff is given by the expected star of indicator function of S of T less than K, and it is probability that S of t is less than K, and it should be equal to phi of minus D2, where D2 is natural log of S0 over K minus R minus delta minus sigma squared over 2 times T over sigma times square of T. And the price of this option is just the present value of it, so it should be e to the minus RT times phi of minus D2. So basically from the cash or nothing call option to the cash or nothing put option, we should have the different side. For the call option, we got the stock price greater than K, but put option we got less than K. So everything which is at D2, we change side to minus D2, D2 hat to minus D2 hat. Everything will be the same except the sign and the inequality size. The third model is assess or nothing call option. This option pay S of t at time t if the stock price is greater than K and nothing otherwise. The payoff function is S of t times what the indicated function, and it should be equal to either S of t or 0, depending on whether the stock price is greater than K or less than or equal to K. The expected payoff here is the stock price times with phi of D1 hat, where D1 hat is natural of S0 over K minus alpha minus delta plus sigma squared over 2 times T over sigma squared of T. Under the rich neutral measure, the expected payoff is given by expected star of indicator function of S of t greater than K and is equal to S of t, probability of S of t greater than K is equal to S0 times e to the minus delta t phi of D1, where D1 is natural log of S0 over K minus R minus delta plus sigma squared over 2 times T over sigma squared of T. The price of this option is S0 times e to the minus RT phi of D1. And number 4, assess or nothing put option. This option is similar to assess or nothing call option, but we just convert the size of the inequality and also the size of D1. This option pay S of t at time t if the stock price is less than K and nothing otherwise. So the payoff function is S of t times with the indicator function, and it should be equal to S of t if S of t is less than K, and it is equal to 0 if S of t is greater or equal to K. The expected payoff is expected of S of t times indicator function of S of t less than K, and is equal to expected value of S of t times probability of S of t less than K, and is equal to S of t times phi of minus D1 hat, where D1 hat is natural log S0 over K minus alpha minus sigma plus sigma squared over 2 times T over sigma times square of T. Under the rich neutral measure, the expected payoff is given by expected star of indicator function of S of t less than K, and is equal to S of t times probability of S of t less than K, which is S of 0 times e to the minus delta t phi of minus D1, where D1 here is obtained by replacing alpha in D1 hat with R, and the price of this option is S of 0 times e to the minus RT phi of minus D1. The Scholes formula. Consider a T-year K-dry European call option on a stock. The payoff here is calculated by the positive function. For the call option, it should be S of t minus K plus, and this result in the maximum value between S of t minus K and 0. It should be equal to S of t minus K times the indicator function of S of t minus K, S of t greater than K, and separate the factor. We got S of t times the indicator function minus K times the indicator function. And similar for the put option, K minus F of t plus result in maximum value between K minus S of t and 0, and it should be equal to K minus F of t times with the indicator function. It should be equal to K times indicator function minus the stock price times indicator function. Now for the Scholes formula for European call option, the initial price of the call option should be equal to S0 times e to the minus delta t phi of D1 minus K times e to the minus RT phi of D2. Remember that phi of D1 represents for the expected value of the indicator function, and S0 times e to the minus delta t represent for the prepaid forward price of the stock price at time 0. And K times e to the minus RT is the prepaid forward price of the choice at time 0. Similar for the put option, we got the initial price of the put option PS0KT is equal to K times e to the minus RT phi of minus D2 minus S0 times e to the minus delta T phi of minus D1. And remember, D1 here is natural log S0 over K plus R minus delta plus sigma squared over 2 times T over sigma squared of T. And D2 is natural log of S0 over K plus R minus delta minus sigma squared over 2 times T over sigma squared of T, and this is equal to D1 minus sigma squared root of T. Applying the pricing formula to other assets, recall that the forward price of the stock price F0TP S should be equal to S0 times e to the minus delta T, and the forward price of the try F0TP is equal to K e to the minus RT. The prepaid forward version of the Scholes formulas is the call option S0KT is equal to F0TPS phi D1 minus F0TP K times phi D2. Here phi D1 represents for the expected value of the indicator function when the stock price is is greater than K. F0TPS is the forward price of the stock price at time 0, and F0TPK is the forward price of the try at time 0. And similar for the put option. Here we got D1 is natural log of the forward price of prepaid forward price of the stock price over the prepaid forward price of the try plus 0.5 times sigma squared T. Remember, for this version we got R is equal to 0 and delta is also equal to 0, so that's why we can basically just have 0.5 sigma squared T over sigma squared T. And similar, we got D2 is D1 minus sigma squared T. And we consider 3 cases when we apply the pricing formula to other assets. The first case is option on stocks with decreed dividends. The forward price F0TPS is equal to S0 minus present value of the dividend. Here the present value of the dividend PV0TDIV is the present value of all the discrete dividends payable over the life of the option. The option on stocks with currency exchange rate is the value of 1 unit of the foreign currency measured in the domestic currency of foreign currency earned interest at the risk-free interest rate RF prevailing in the foreign country. Suppose a foreign country has a time 0 exchange rate of X0 units of domestic currency per 1 unit of foreign currency. The forward price, the prepaid forward price of X is X0 times expected value of minus RFT. Option on futures. The prepaid forward price for a future contract is just the present value of the future price, that is F0 times e to the minus RT. And once you have the prepaid forward price for stocks, we just replace it into the Scholes formulas to evaluate the call option and the put option price. Alright, so let's consider the first example. Consider a stock that follows the Scholes framework. You are given the current stock price is S0 is equal to 100, and the stock pays dividend continuously at a rate proportional to its price. The dividend yield delta is equal to 1%. The stock volatility is sigma is equal to 0.2. The continuously compounded risk-free interest rate is R is equal to 0.04. Calculate the price of the following option, which all matures at t is equal to 0.5 and have a choice of k is equal to 90. A cash or nothing call, a cash or nothing put, an assess or nothing call, an assess or nothing put. So for this problem, we are given S0, delta, sigma, R, T, and K. So we have to use the formula in order to calculate the price of these options. And before we calculate the prices of these options, we have to first calculate D1, D2, phi of D1 and phi of D2. D1 here is natural log of S0 over K minus R minus delta minus sigma square over 2 times T over sigma square of T. Here S0 is 100, K is 90, R is 0.04, delta is 0.01, sigma is 0.2, T is 0.5. So we got D1 is 0.921788, and D2 is just D1 minus sigma square of T, so it should be 0.780367. From here we use the standard normal distribution to calculate phi of D1. Phi of D1 here is probability that the standard normal variable less than D1, and it should be 0.82168. This number can be calculated using the calculator or using the standard normal distribution table. And similar, we got phi of D2 is 0.78241. Now we calculate the prices of these options. The first one, a cash or nothing call. This one, the price of it should be e to the minus RT phi of D2. It should be e to the R here is 0.04 and T is 0.5. So RT is 0.02. So we got e to the minus 0.02 times with phi of D2, which is 0.78241. To bring it down here, we got 0.76692. That is the price of the call or nothing call, a cash or nothing call. Similar for the cash or nothing put, we simply just have to switch the sign of D2 to minus D2. So it should be e to the minus 0.02 times with 1 minus 0.78241, and it should be 0.21328. This is simple statistics, so I don't need to explain clearly how I get this number. It's very clear. C, an assess or nothing call. For this one, we use the formula for the assess or nothing call, of course. We got S0 times e to the minus RT phi of D1. S0 is given as 100. RT is 0.02. Phi of D1 is 0.82168 from the last calculation. So the price of an assess or nothing call should be 81.7882. And similar for part D. For part D, we basically just have to flip the sign of D1 and C and part C, and it should be 17.74306. You can do it by yourself. I repeat, for D, S0 is given as 100, R is given at 0.04, T is 0.5. D1 here is replaced by minus D1. Minus D1, phi of minus D1 is just 1 minus phi of D1. So it's very easy to calculate. Now example 2. Consider a non-dividend paying stock that follows a Black-Scholes framework. You are given the current stock price 100, the stock volatility is 0.2, the continuously compounded risk-free interest rate is 0.04. Consider a contingent claim that matures after 1 year. Let S1 be the time 1 price of the stock. The contingent claim pays 10 if 110 is less than S1, less than 120, and pays 20 if S of 1 is greater than 120. It pays nothing if S of 1 is less than 110. Calculate the price of this contingent claim. This is a little tricky problem because it's a combined option. If we look clearly, we see there are 3 cases, right? First, if S of 1 falls into the ranks from 110 to 120, the claim pay 10. If S1 is below, above 120, we pay 20. If it's below 110, we pay 10. We pay nothing. So basically, we can consider this is like a combination of two separate options. If we consider the first option is using K is 110, we see that we pay nothing if the stock price is less than 110, and we pay 10 if the stock price is greater than 110. And if we consider the second option as paying 10 if S of t is greater than 120 and nothing when it's less than 120, then we have another option. So when we combine these two options, when the stock price is less than 110, the first option pay 0, and the second option pay nothing. So that means when the stock price is less than 110, we pay nothing. If the stock price falls between 110 and 120, the first option pay 10, but the second option pay nothing. So we still have 10, and we have to pay 10. If the stock price is greater than 120, the first option had to pay 10, and the second option have to pay 10. So we have to pay 20. See that? So that's the idea. This claim can be considered as a combination of two cash or nothing call options. One pay 10 if S of 1 is greater than 110, and the other pay 10 if S of 1 is greater than 120. So now we calculate the value of each of these two options and then add them up. So for the first option with K is equal to 110, we got D2 is natural of 100 over 110 plus 0.04 minus 0.2 square over 2, the whole thing over 0.2. The reason for this is because we consider S of 1, so T is 1. So there's no square root of 1 because for square root of 1 we don't have to write down. Delta here is given and is not given, that means 0. R is given as 0.04. See that? So D2 is minus 0.376551. So from here we got phi of D2 is 0.35325 using either the standard normal distribution table or just use the technology calculator. The value of the first option, remember this is cash or nothing call option, so we got first of all the 10 is the factor, right? 10 times with the price of 1 unit of the cash or nothing option. So we got 10 times e to the minus RT, phi of D2. R is 0.04, T is 1, phi of D2 is 0.35325. We got 3.393599. This is the value of the first option. Now should repeat for the second option. For the second option, the threshold is 120. So we use K is 120. And similar, we repeat all the steps. We repeat all the steps. We got D2 is minus 0.811608, and phi of D2 is 0.20851. From here, the value of the second option is similar to the first option. We got 10 times e to the minus RT, phi of D2, which is 2.00334. The total value of this option is the sum of D2. So we got 3.39 plus 2.00, which is 5.39.